This captures high-density operations at night. Dozens of aircraft traveling hundreds of miles per hour, converging on a single strip of pavement in total darkness. Every square foot of an airport operates as a layered, multi-channel data transmission system, broadcasting spatial orientation directly to the pilots navigating it. Misinterpreting this data matrix carries immediate consequences. A single missed cue can result in a runway incursion, where an aircraft taxis directly into the path of another taking off, or a mid-air collision in the surrounding traffic pattern. To understand how aviation maintains its safety record, we have to deconstruct this infrastructure from absolute first principles, removing every light, line, and procedure until we are left with empty land, and then rebuild it. We will analyze three specific data layers: the painted genometric surface markings, the optical physics of the glide path projectors, and the procedural radio architectures governing the airspace above. When traveling at high speeds with restricted visibility, human sensory perception degrades. This overlapping redundancy forces the environment to do the processing for the pilot, guaranteeing safe operations regardless of the weather. We begin with a blank strip of asphalt. To integrate this into the global network, it requires a standardized identifier. Runways are named strictly by their magnetic direction, rounded off to the nearest 10 degrees. A runway facing 274 degrees magnetic becomes runway 27. In this diagram, we upgrade the asphalt to a precision instrument runway. We add the threshold markers indicating the beginning of the landing surface, followed by the touchdown zone and the aiming point markers located exactly 1,000 feet down the strip. Sometimes, obstacles prevent aircraft from landing at the very edge of the pavement. A displaced threshold is marked by white arrows pointing to a thick, solid line. Aircraft can use this section to taxi or begin their takeoff roll, but they are strictly prohibited from touching down here. If you see yellow chevrons instead of arrows, the surface is structurally unusable for normal operations and serves only as a blast pad or a stopway for an aborted takeoff. Moving off the runway, the geometry shifts. This top-down view of the taxiway reveals a continuous yellow center line, flanked by two continuous yellow edge lines precisely 6 inches apart. Aircraft must keep their nose wheel pinned to that center stripe. Eventually, that taxiway intersects the active runway, bringing us to the most critical ground marking in aviation, the hold short line. It consists of 2 continuous and 2 dashed yellow lines crossing the entire width of the taxiway. The geometric rule here is rigid. An aircraft approaching from the solid line side must come to a complete stop. An aircraft exiting the runway from the dashed line side is clear to cross without clearance. To reinforce this physical barrier, a runway holding position sign is placed adjacent to the line. It features white characters on a red background, visually telling the pilot to hold their position until air traffic control grants permission. During days with extremely low ceilings, pilots rely on Category 2 instrument landing operations. Because the electronic signals guiding those arriving planes are highly sensitive, departing aircraft must hold at specific Category 2 holding points, located much further back from the runway edge to prevent signal interference. These geometric patterns form a passive, standardized barrier. They require no electricity and no radio calls, yet they dictate the physical flow of multi-million-dollar machines to prevent catastrophic runway incursions. When the sun sets or heavy fog rolls in, ground paint becomes useless. The airport must switch to an illuminated spatial matrix. At many uncontrolled fields, the lights do not stay on all night. Instead, they use a decentralized pilot-controlled lighting system. The pilot uses their onboard NavCom radio to activate the airport's grid from the air. The activation protocol is highly specific. By tuning to the published frequency and keying the microphone 7 times within 5 seconds, the pilot triggers the lights at maximum intensity. The system automatically holds that illumination for a 15-minute window. Once activated, this isometric layout ignites with a strict color code. Taxiway boundaries are defined by omnidirectional blue edge lights, while the exact center path is marked by a line of green lights. Transitioning to the active runway, the blue edge lights are replaced by high-intensity white lights. The runway end lights utilize a split-color lens, displaying green to incoming aircraft to mark the safe threshold, while showing red to planes rolling toward the far end. On advanced precision runways, pilots also rely on the runway centerline lighting system. These flush-mounted fixtures are bright, solid white lights embedded directly into the pavement. As a landing aircraft decelerates, it means to know exactly how much pavement is left. At exactly 3,000 feet remaining, the centerline lights shift to an alternating pattern of red and white. When only 1,000 feet of usable surface remains, the lights change completely to solid red, signaling the imminent end of the runway. This color transition allows a pilot moving at over 100 knots to calculate their remaining stopping distance purely through their peripheral vision, keeping their focus entirely outside the cockpit, where it belongs. Aligning with the horizontal runway is only half the equation. In total darkness over an unlit landscape, a pilot has zero visual reference to judge their vertical descent angle. The Visual Approach Slope Indicator, or VASI, utilizes engineered optical projectors to emit discrete visual corridors upward into the approach path, typically set at a 3-degree slope. As the aircraft moves vertically through the airspace, the lenses filter the light based on the plane's exact physical altitude. Fly above the proper slope and you see 2 white bars. Drop below it and both bars shift to red. To guarantee clearance from ground obstructions, the pilot must maintain the exact boundary between the 2 beams. When perfectly on slope, the near bars appear white and the far bars appear red. Modern airports often replace VASI with the Precision Approach Path Indicator, or PAPI. As shown in this pilot's eye view, PAPI condenses the information into a single horizontal row of 4 light units adjacent to the touchdown zone. PAPI operates on proportional logic. If you are entirely above the glide path, all 4 lights shine white. As you descend onto the correct 3-degree slope, the inner 2 lights shift to red, creating a perfect 2 red, 2 white split. If the descent rate increases and you dip slightly below the safe corridor, a 3rd red light appears. Drop further and all 4 lights burn red, signaling an immediate risk of impacting terrain. These optical systems take a continuous, highly variable data point, the aircraft's descent rate, and simplify it into an immediate, binary visual feedback loop. Having secured the descent and the landing roll, we zoom out to the macro level. The airspace surrounding the physical runway is governed by strict, invisible procedural boundaries. At uncontrolled airports, aircraft organize themselves using this standard rectangular traffic pattern. Unless otherwise published, all turns are made to the left, establishing an orderly, predictable flow without any air traffic control intervention. The pattern is broken into 5 distinct procedural legs, flown typically 1,000 feet above the ground. The upwind climb, turning onto the crosswind leg, running parallel on the downwind leg, turning base, and finally aligning with the runway on final approach. Pilots continuously broadcast their position on a common frequency, allowing everyone in the airspace to build a mental map of the traffic and self-regulate their separation based entirely on geometry. Controlled airspaces operate on a completely different model. Within Class B, C, or D airspace, ATC utilizes terminal radar to actively assign altitudes and headings, manually sequencing incoming traffic. When ATC calls out approaching traffic using the clock system, advising a pilot of an aircraft at their 2 o'clock position, they are referencing the radar screen. As this diagram shows, radar only tracks the actual ground path over the Earth, completely ignoring where the aircraft's nose is physically pointing. If a pilot is crabbing sideways into a heavy crosswind, their heading and their ground track are completely different. To actually spot the traffic ATC is calling out, the pilot must actively calculate their wind drift and adjust their visual scan accordingly. Faster, more urgent tone. Consider an aircraft approaching a highly congested, controlled airport at night when the radios suddenly die. Total communication failure. The pilot instantly initiates the mandatory lost comms procedure. They remain outside the controlled airspace, dial the emergency code 7600 into their transponder to silently alert radar controllers of the failure, and maneuver to enter the visual traffic pattern. With the primary digital and vocal data streams severed, air traffic control immediately falls back to a centralized analog system, a high-intensity directional light gun aimed directly at the cockpit from the tower window. In this matrix chart, the flashes of light act as absolute commands. A steady green light authorizes the pilot to land. A steady red light means they must give way to other traffic and continue circling. Now calculate the pilot's final workload. This infrastructure functions as a dynamic, overlapping matrix of redundant information, built to verify and cross-check human spatial awareness. Translating surface geometry, optical projections, and procedural protocols allows pilots to maintain safe separation and precise alignment when visual and radio cues are at their limit.